Hey everybody, this is Larry. This is me going with Q2 of the weekly contest 458. Minimize maximum component cost. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Honestly, this reminded me of something that we did like very recently. I don't even know what's going on. I mean, I feel like we had a minimum spanning tree problem like a week ago or 2 weeks ago, right? Something like that. So to me, it was very fresh on the mind, and I was able to solve it very quickly. But also, some part of it is just having an understanding of minimum spanning tree and connected components and stuff like that. In general, I guess they actually now that I think about it, or now that I've read this more differently, even though I immediately jumped to minimum spanning tree, but it doesn't have to be. So maybe that's the thing that is quote unquote different. But then, yeah, I didn't even realize that there wasn't a spanning tree, but because edges could be really big and it doesn't have to be a tree even. So maybe that's what's different. By the way, is the same idea, which is that the cost of the component is defined by the maximum edge weight in that component. That, of course, is the definition of the spanning tree, or in perhaps a forest, but it is the definition of that tree. You can, and this is, yeah. So actually, now that I think about it, now that I read it this way, I think I messed up. I mean, I did, just to be clear, I did solve this in about 3 minutes, and I'm very thankful that it did not time out. But I believe that all you have to do is sort and use Kruskal, or is it Kruskal or the other one? I always forget which one. Oh no, it's Kruskal. Yeah, and I think, yeah, the first time you dip below K, that's it, right? Let's actually solve this. I actually honestly solved this with Union Find, and you can actually solve this with other connected components thing with binary search. The idea is that, well, you binary search on the edges to remove. Anything above your target or greater you remove. So that means that you keep the stuff that is less than target. And yeah, and binary search will do. You could say that this binary search is linear in the number of edges, but that's going to be most cases. Like if you could also implement this using depth first search or breadth first search, two other standard ways of getting connected component with a new implicit graph with all the edges that are only under or equal to target. And yeah, and this is the very straightforward binary search. Not gonna go over it in this video, but it turns out I don't think you even need it. I think for this particular problem, you can actually just use Kruskal, and I mean the complexity is going to be slightly, I want to say slightly better. Is that even true? I guess it's mostly similar. And what I mean by that is that with binary search on 0 and 10 to the 6, where you use Kruskal, you have to sort the edges, which we do not do here. So maybe that's slightly faster, or slightly different, or the complexity is slightly different. But you could definitely use Kruskal. And let's actually do that now. We keep our union fine. This will be the upsolve. But yeah, I don't know I have that much to explain, so let me see if I can explain before I solve, right? Is that with binary search, and it is just that if you create and more than K components, then you need lower of your maximum edge, right? Because we're always thinking about maximum edges. In this case, that means that we cannot have any edges in the entire graph that is greater than this target that we're testing for. And that's really it, just a binary search. But we don't even need to, maybe, unless I'm like really wrong. Let's try for upsolve. We can do a Kruskal. So this is the union find things, right? And then maybe we do a edge dot sort. We do a key lambda x, we sort, or syntax is wrong, we sort by the edges, right? Yeah, we sort by the weight, that is. And so that's what we sort by. And yeah, and then we just kind of connect. We don't need this. If they're not this, we yeah, if the edges create an or connect two different components, then we subtract one component. And then yeah, if count is what is sorry. K could be n or what? Oh, I think I have to kind of think about it. That's all. But I guess in this case there is edge cases, which is that if count is greater than or less than k, then we want to return. Is it 0? Oh yeah, if a component has no edges, then it's called a 0. So we okay, then it just returns. Ooh, what happened? There's some shortcuts that keyboard shortcuts that I keep hitting by accident. Okay, we return 0. Otherwise, if count is then we return weight, and then that's it. I think 4 5 looks okay. Let's give it a submit. But yeah, so it turns out that this is just minimum spanning tree, and I overdid it a little bit, but during the contest. But keep in mind the context is that I'm trying to solve as quickly as possible. I did it in 3 minutes, so I didn't make this reduction. But yeah, you could just sort the edges. But the reason why it is similar is because it's just not. How long did it took? Oh, it took way faster, to be honest. Because the other one, I think. Okay, I don't know how. Oh. What is going on? Oh, it doesn't even show up. Okay, fine. My point is, the other one took like 3 seconds, I think, or something like that. But in any case, yeah. So minimum spanning tree is actually the more optimal answer. I know that this video is structured a little bit weirdly, but I am, these videos, I do try to give you my perspective, the way that I solve it, right? Because the solutions, you could find it anywhere on YouTube's. Or even Leetcode or whatever. So I'm trying to give you my idea, and my idea, of course, is that I'm trying to optimize to finish quickly. And I did it in 3 minutes. So I did a binary search. The binary search solution. I don't know why Leetcode is being weird, but if you go back to it, the binary search solution is going to be ye log r, where r is the range of the numbers from 0 to 1e6. Where this is going to be ye log ye, where, well, it just scales a little bit cleaner, but yeah, I mean, as you can see, there's like 8 times faster given their inputs, but still, the other one is fast enough. But I definitely could have, given different inputs, definitely could have time out on it, and I would have deserved it, to be honest, because I think this is, well, I don't know. But yeah, now put it this way, this is a standard minimum spanning tree problem. I don't know why I didn't. I just kind of. I think the reason why I did binary search, honestly, is because of that problem that we did a couple of weeks ago with the binary search. So I was like, that was way fresh on my mind. If I didn't, maybe I would have found a minimum spanning tree. But I also happen to know that that one would have worked mostly. And it took me 3 minutes again. I mean, I'm saying the 3 minutes not to brag, but to just show that that's why I knew, because if I had more time, then maybe I would have optimized it down, and I'm like, oh yeah, actually this could be ye log ye, and it is a minimum spanning tree, but it takes longer time, and you have to kind of reason it and prove it a little bit and so forth. So yeah, that's it. That's what I have for this one. This is ye log ye after the Kruskal's minimum spanning tree algorithm. I'll write it out. I think it's. I hope I'm spelling that correctly. I missed an R. But yeah, it's been a while. And this uses union find, which I'm also not going with in this video. This union find is a standard topic that you should be able to find a lot of YouTube videos for. So definitely do that. And that's it. That's all I have for this one. Here's my union find. And here's my, well, just joining the union fine. So yeah, that's it. That's what I have. You can look up the binary search one too. I don't know why it doesn't show in my submission. I have to like go for a lot of clicks to get it. So, but the binary search is very similar. You saw how I edited it. So yeah, that's it. That's all I have for this one. Let me know what you think, and you can watch me solve it live in the contest now. So go. Okay. Oh, the other ones. Not bad for medium. That was kind of easy, but you know, what recording? Okay. Given graph, any number of k connected components, the cost is find the maximum rate on that component, minimum possible value of. Okay, so just binary search, right? Yeah. Okay, fine. It's very awkward, but it's just binary search and Kruskal, I guess. Okay, then yeah, pretty straightforward things. K components. Okay, yeah. There are ways you can do it, but let's do it the dumb way. And I'm not ready for this. It's maybe I should have done a warm up. This is just right. Okay, so then now we go you read W and edits. If you find view, nope. With weight is less than or equal to target. And components. Okay. That's it. Okay. And then now we can, what is pot? At most k components. So that's it's true if this is that. Left is equal to 0, right is equal to. Technically, you could binary search on the edges, but whatever, it's fine. It's like 10 to the 5th, 10 to the 6th. I mean, if it times out, I blame it on Leetcode. Should be fast enough. But if Leetcode doesn't want it to be, I guess it doesn't have to be. Okay, if it's good, then we want to try something smaller. Four, 5, all right. Hopefully I didn't misread it. Okay, didn't misread it. It was very easy to misread. Well, I just kind of probably. Hey everybody, thanks for watching. Hit the like button, hit the subscribe button, join me in Discord, let me know what you think about this problem, this video, this contest, everything in between. Stay good, stay healthy, to mental health. I'll see y'all later and take care. Bye bye.